Thank you. Hello.
Well, actually, I was there like 3:30, so I got it early, but I've been happy with family. So that email was family. Oh, yeah. Oh, yeah, sorry, done.
All right. So who's ready for our reading break? All right. So, yeah, so thanks very much for your assignments. If you haven't done so, please bring up your solutions. And then I don't have it ready right now, but I will have an assignment 3 ready to go. I'm not going to make it obviously due right after the break. I'll probably make it due the Friday after we come back. So if you don't want to work on it over the break, you're studying for other things or just relaxing, that's totally fine. But just watch for that. I will probably get it posted, maybe over the weekend or early during the reading break. So the sorts of things that we've been talking about is the Gaussian distribution. So there it is. It depends on a mean and a standard deviation sigma. The features of the Gaussian distribution are that it is peaked at the mean and it falls off symmetrically on either side of the mean. And the width of that distribution is characterized by the standard deviation sigma. We did a kind of little example problem where we asked the question, what is the probability of a measurement falling between two values, x1 and x2? See ya. And it was by taking this integral of the Gaussian distribution between those two limits. And so if we make the limits, say, plus and minus infinity, then that would have to evaluate to 1, because that would be like the probability of a measurement falling anywhere has to be equal to 1. If we made the limits x1 and x2, say mu plus or minus a single standard deviation, then evaluating that integral would give you a probability of 68%. So 68% chance of a measurement falling within 1 standard deviation. Within 2 standard deviations of the mean, that comes up to 95%. And then 3 standard deviations of the mean, is 99.7% of your measurements should fall within that range. So when you do an experiment and then you find that your result is more than one standard deviation away from the expected value or what we might call the mean, that doesn't necessarily mean that anything's wrong. That should happen 32% of the time. But if you start finding that your result is 2, 3 standard deviations away from the expected value, then you start to maybe sweat about it a little bit. And then we also talked about how in, say, particle physics, if they're going to announce a discovery of a new particle or something like that, they wait until they get like to 5 sigma, so 5 standard deviations away from the mean. And so what they're really saying is that there's very unlikely that what we are reporting is a result of some random statistical fluctuation in the data. And so I think I forget exactly what the number is, but it's more than like a 1 in a million chance of that happening. So before we move on, I thought we would just go through and just summarize all of the probability distribution stuff that we've talked about. What we started with was the binomial distribution, and the reason we started with the binomial distribution is that it's one that we could calculate or derive from first principles. And it's also pretty common, like we were able to connect it to like Brownian motion and things like that. So there is the binomial distribution. It involves all these factorials, and little p is the probability of a success in any single trial. We calculated the mean of the binomial distribution, and was just the number of trials times the probability of success of any given trial. So if you roll a die 6 times, the probability or the average number of times that you're going to get, say, a 2 is 6 times 1/6 probability. And so it becomes 1. So you expect to get that once on average in 6 rolls. Of course, if I do 6 rolls, it's possible that I get 2 6 times, or it's possible that I get 2 0 times, but on average, you should expect to get it once. The standard deviation was n times p times 1 minus p. Okay. Then what we did is we used the binomial distribution to derive the Poisson distribution. And the limiting case that we were interested in is when the probability of success is very low. We were able to do a series of approximations, which led to this Poisson distribution, which has this form of mu to the x, e to the minus mu, all divided by x factorial. What we found is that the mean and standard deviation are characterized by a single parameter, mu. So the mean is mu, and the standard deviation was the square root of mu. This, in physics, is particularly relevant for counting experiments. And we'll talk about that a little more today. So, for example, in Brownian motion, you are doing a counting experiment. If you count the number of particles you see in your picture that you take as a function of height through the suspension, the uncertainty in the number of counts is going to be the square root of the number of counts. Okay. All right, and then what we just finished was the Gaussian distribution. Again, we started from the binomial distribution. This time it was a little bit harder, but we made a series of approximations. And the limit that we're interested in is a large number of trials, so n is large, and the number of successes, n times p, is also relatively large. And really what that's, the binomial distribution is asymmetric when x is close to 0, so the number of successes. So what we're really doing here by saying the number of successes is large is we're moving that away from x equals 0, which leads to a symmetric distribution. And that's why we ended up with this form of the Gaussian distribution, which is an a distribution that's symmetric about x minus mu. Okay, and so here we had two parameters characterizing this distribution. The mean mu is the peak of the distribution, and standard deviation sigma is how wide it is. All right. So what I want to do is, oh, I better get my notes. I want to talk about counting experiments here just briefly, and then we're going to talk about propagation of error. Okay, and this is all going to be eventually related back to the Gaussian distribution. So almost everything else we do for the rest of the term will basically be based on the Gaussian probability distribution. Okay, so in a counting experiment, at first glance, you might say, I'm good at counting. I can count the number of things exactly. What are you talking about? Like, why is there an uncertainty when I count 7 marbles? There are 7 marbles, right? So here's what I mean. So in principle, we can measure the number of events in a time interval delta t with absolute certainty. Okay, to make this example a more of a physics example, let's imagine you are doing the Brownian motion experiment. So you're looking under a microscope at these particles suspended in a solution, and you're looking at a certain depth within that solution, and you see, okay, I can count that there's exactly, I don't know, 25 particles in my view right now. So what you could do is you could say, all right, I'm going to prepare like 20 different identical slides. I prepare them in exactly the same way at exactly the same time. I let them rest for the same like 12 hours. And then after 12 hours, I look at each one of them at the exact same height within that suspension. And in the first one, I get 25, but the other one, I get 28, and then I get 18, and then I get, I don't know, 23. And so all of these identically prepared samples should behave in the same way. But when we go and say count the number of particles at a certain height, we get a different answer every time. And so that's what I mean by uncertainty in the number of counts. If you imagine doing the experiment over and over and over again in exactly the same way, you're going to get a distribution of results. And so for a counting experiment, that distribution will follow the Poisson distribution. Okay, so however, if we repeat the measurement many times, oh, sorry, what do you?
The third word.
Can, yeah, it's just can, yeah, sorry. Yes, no problem. Repeat your measurements many times. We will get statistical fluctuations. In the number of counts. Okay, so for example, we could make a table of the trial. Maybe this is the slide number. So we have all these different slides, and we count the number of particles at a certain height inside that little chamber of the suspension. And so we get, I don't know, 18, 24, 21, 19, whatever, something like that. And so we get, a different result every time. We could make a histogram and we could plot the results, and we would get some kind of distribution. And so this is the number of counts here, and this is the number of, say, occurrences. So by number of occurrences, I mean, how many times did we get an 18? And how many times did we get 24? How many times did we get 21 out of our N trials? Okay, and if you plot that distribution for a Poisson distribution, it might be an asymmetric distribution, and the mean is going to sit around here. So it'll sit to the right of the peak. And so this is where our average sits. So this is the Poisson distribution of counts. All right. Now, the problem is that if I'm doing a Brownian motion experiment, I don't want to make 1,000 slides and count the number of particles at every single at some height in the chamber, because what I want to do is I want to is what we do in a lot of cases is say, all right, I'm going to do, oh, that's not good. I'm going to do the experiment once, and I'm going to assume that the number of counts I made is a reasonable estimate of the mean. It's not going to be equal to the mean, right? I could get unlucky and I could make a slide where I count something that's way out at this tail, and that's quite far from the mean, and it's not a good estimate. I don't know that because I haven't done the experiment 1,000 times, but it's what I'm going to do, okay, for practical reasons. Okay, so here we would get also that the standard deviation of the mean is sigma is equal to square root mu. Okay, so in practice, we often cannot make many repeated experiments to map out the full distribution in order to properly estimate mu. So therefore, in counting experiments, we will often do the measurement once and assume that our results is a reasonable estimate of mu. I mean, in fact, what's likely to happen is our result will probably most likely or most often will sit near the peak of the distribution, right? That's where the probability we're most likely to get a result near the peak. And so if our distribution is asymmetric like this, then we probably underestimate mu by a little bit. That's probably what happens in most cases. Okay, so we assume that mu is equal to n, where n is, say, the number of counts that we've made in whatever the experiment is. I've been using the example of counting suspended particles, but it could be the amount of beta decays in a time interval, or the number of times you observe a muon going through your particle detector in some time interval, something like that. So we assume that mu is equal to n. And if we do that, we know the standard deviation is the square root of mu So we assume that sigma is equal to the square root of n, if n is our best estimate of the mean. So that's why if you did the Brownian motion experiment where you had to count particles, I've been telling you to use as the estimated uncertainty in the number of counts, the square root of the number of counts. Okay, does that make sense? Was that clear enough? Yeah. Okay, good. So what I want to do next is I want to talk about propagation of errors. So some of you may have, well, you should all be somewhat familiar with propagation of errors, at least, you know, if only from, say, first year labs. If you took 231, we would have talked about that briefly as well. But let's do it more formally right now. So propagation of errors. So I want to just motivate this by giving you a bit of an example. So let's suppose we want to determine some quantity y that depends on measured values or measured parameters. Let's say u plus or minus some uncertainty in u and v plus or minus some uncertainty in v. So the question is, if y is equal to a function of u and v, what is the uncertainty in y? Okay, so to make this like a little more concrete, a little less abstract, we can talk about one of the experiments that's available in the lab. So, for example, in Boltzmann's constant, let's see. You measure a current I, and the ln of I is approximately equal to the ln of I naught, some constant, and plus E over kBt times V, where V is a voltage, T is temperature, E and Kb are constants. So what you end up doing is you measure the current as a function of this voltage. It's a transistor circuit, so you're measuring the current into the collector of the transistor as you vary the voltage at the emitter. Anyways, those details don't matter for what we're talking about. But if you were to make a plot of the ln of the current as a function of voltage, it would be a straight line. The intercept would be ln times this I naught, and the slope would be this E over kBt. So if you plot ln of the current versus this voltage, the slope is equal to m, we'll call it, is E over kBt. So what we're going to imagine is you've done the experiment and then you've come up with an estimate of the slope and the uncertainty in the slope. And you've also come up with a measurement of T, the temperature, and its uncertainty. So let's assume that you've determined m plus or minus its uncertainty and T plus or minus its uncertainty. And what we're going to try to do is we're going to try to calculate, let's say we're trying to find Boltzmann's constant, right? We call it Boltzmann's constant experiment. So we're going to say we know E either from just looking up the value, or maybe you've done previously like a Millikan oil drop experiment or something, and you know the charge of an electron. So now you want to calculate Boltzmann's constant, and we assume that E is known. Okay, so, well, let's see, that's pretty easy. Boltzmann's constant is just going to be E divided by M and divided by T. Okay, so now Boltzmann's constant is a function of M and T, and we know M plus or minus sigma M and T plus or minus sigma T. And so the question is, what is the uncertainty in Boltzmann's constant? Okay, and so in first year, what we would have done is we would have said, oh, I see, this is like, there's a multiplication division kind of rule. And so we have two divisions. And so what we're going to do is we're going to add the fractional error. So KB, the uncertainty in KB divided by KB is going to be equal to the uncertainty in M divided by M plus the uncertainty in T divided by T. And so we want to see if we can recover that kind of result and see if that's exactly right, or whether we want to modify that or whatever. Okay, so that's a bit of the motivation. So what I'm going to do is I'm going to go back to the more abstract problem where y was a function of u and v, and we know u plus or minus sigma u and v plus or minus sigma v. Okay. Well, actually, sorry, I'm not going to do that. We are going to do that, but I'm going to start with an easier example first. Let's start with a function of a single variable, and we know u plus or minus sigma u. And so we want to find the uncertainty in y. Okay. So recall that if we have a function of one variable, we can approximate, say, f of u as a Taylor series. So what is a Taylor series expansion here of f of u? How would you express the Taylor series? I only want to keep the first two terms. What are the first two terms? Yeah, there's fu, right? Plus the derivative. Yeah, that's right. So if you said that this function was going to be equal to, let's see, I'm going to write it in this way. So we're going to do a Taylor series expansion. Here, we'll write it probably the way a math person would write it. Okay, so we take our function, and this is an expansion about u bar. So often people will write their Taylor series expanded about 0. So you would have f at 0 plus u times the derivative of f evaluated at u equals 0. That's a Taylor series expansion about u equals 0. This is a Taylor series expansion about u is equal to some u bar that we can arbitrarily pick. So this is a Taylor series expansion about u is equal to u bar. Okay. So what we're going to try to do is we're going to try to manipulate this in such a way that we can estimate the standard deviation of y is equal to f of u. Okay, so the first step is we're going to assume that f evaluated at U bar is approximately equal to F average. So let's imagine, maybe we made a whole bunch of measurements of U and then we average them, we find the mean of them. So maybe that's what we mean by U bar. What we're going to assume is that if we were to calculate the value of F at each of our measurements of U and then average F, that these two are similar. They're going to be exactly the same if this is a linear function, but they may not be exactly the same if they're nonlinear, but we're going to assume that they're going to be close to one another. Okay, so if we do that, then we would say F is equal to F bar plus U minus U bar times the derivative of F evaluated at U bar. Okay, and so we're just going to make some little manipulations here. So therefore, F minus F bar is equal to U minus U bar F prime at U bar. Okay. So that's going to be U minus U bar, and then we'll write this as df du evaluated at U bar. So here I have some function minus its average. How do you calculate standard deviations? So if I made a bunch of measurements of X and I calculate the mean of those measurements, how would I calculate the standard deviation? So that's for the binomial distribution, but I just want like the straight, like first year standard deviation calculation. So you would take X minus mu, then you'd square, oh, you're back. Look at that. Okay, X minus mu, and then you would sum over all of your trials. And then what do I have up front? 1 over n minus 1. And so then we would take the square root of all of that stuff. So this is the standard deviation. So that's the standard deviation of X. So what I'm going to do is I'm going to apply the same sort of calculation to F minus its average. And so I could define like a sigma F, or yeah, I'll define, so this is the definition of standard deviation. Okay, so in a similar way, we can find sigma F as, in fact, what I'll probably do is I don't want to write all these square roots all the time. So I'm going to calculate sigma F squared. Well, what we would do is we would take 1 over n minus 1. So however many measurements of U we made, then I calculate F of U at each one of those values, and I average that, and I'm going to get an F bar. And so I'd have an F bar over here. I would take my individual measurements, I would take that difference and I'd square them, and I'd put in a sum from I equals 1 to n, something like that. Now this will be Fi, the value of our function evaluated at wherever Ui was, whatever the result for the ith measurement was. Okay, so fair enough. But if you look, this F minus F bar, we've expressed in this way. And so what we're going to do is we're going to take that and we're going to sub it in here. Okay, and so what happens if we do that? We're going to have sigma F squared is equal to 1 over n minus 1. We're going to have the sum Okay, and so now we're gonna have u minus u bar times df du evaluated at u bar. And then we have to square all of that. Okay, so this is 1 over n minus 1. The sum of I equals 1 to n. So let's just evaluate the square. So, I mean, all we have is two factors here, so we can just square them individually. So this would be u minus u bar squared. I should have a little subscript I here, right? Because we've done a whole bunch of trials. And then we'd have our df du at u bar squared, like so. Now, what's interesting about this is that this is a sum over I, but only this first factor involves anything to do with I. This is just some function, we take a derivative and we evaluate it at some specific point. It doesn't depend on the individual measurements, it just depends on the average of all of the measurements. So the sum is acting only on that first term. So we could write this as sigma f squared. Let's just emphasize that this is independent of I. Here, I'll give myself a little more room. So therefore, sigma f squared is equal to, I'm going to put some brackets here, 1 over n minus 1. The sum of I equals 1 to n. Ui minus u bar squared. And then I'll close the bracket. And then we just have to multiply by df du at u bar squared. Okay. What's this thing in the first set of brackets? Exactly. That's exactly what it is. So this is sigma u. It's the standard deviation of u squared because we don't have the square root in there. Okay. So therefore, sigma f squared is equal to sigma u squared times the derivative of f evaluated at u bar. And so this is our propagation of errors for a function of one variable. Function. Yeah, you could. Then the only thing you'd have to be careful of is that when you take the square root, you can get positive and negative roots. And so uncertainty estimates are always positive, so you would just put absolute value signs around your derivative. Yeah. So yeah, that's exactly true. We could write this as sigma f is equal to sigma u, absolute value of df du at u bar. And so that is also correct. Okay, but what I want to do, of course, is I want to move on to functions of more than one variable. Before we do that, what I'd like to do is see if we can interpret what this is actually meaning. So let's suppose that what we have here is a plot of our function f of u, and here's u. I don't really care what this looks like. It could be complicated, arbitrary, whatever you want it to be. So let's suppose that you did your experiment and you find that the average, so what you are actually going to measure is u a whole bunch of times. And so you make all these measurements of u and then you find the average value and it sits right here. So there's u bar. What does df du represent? The slope of what? Of what line? Yeah, it's a tangent line at wherever you're going to evaluate your function. So that's exactly right. So if we're evaluating our function here, what I'm going to do is I'm going to draw a tangent line. And so we'll draw our tangent line like so. And this is df du evaluated at u bar. And if we go across to our axis over here, this is f evaluated at u bar. Okay, fair enough. So now we have this part of our expression, sigma u represents kind of the range of values of u that we got. Like a typical range of values, 68% of our measurements fell within one standard deviation of mu. And so what we have here is, I'm going to exaggerate it a little bit. So this would be u bar minus sigma u, and over here would be u bar plus sigma u. And so this is going to span 2 sigma u. All right. So if we then bring this back over here, we could identify this intercept on our vertical axis as f at u bar, or let's just call it f bar minus sigma f. And over here would be, oh, I'm going to move this. So let's see, I want to put, say, f of u here. And this is going to be f bar plus sigma f. And so this range is 2 sigma u. This range is 2 times sigma f. And they're just related by this straight line. This is a rise, this is a run, and so rise over run gives you slope. It must be equal to this slope here. So for the red line, the slope is rise over run, which is equal to 2 sigma f over 2 sigma u, and it must also be equal to, and must also equal, let's see, df du at u bar. And so, of course, we can cancel the factors of 2. And so therefore, sigma f over sigma u is equal to df du u bar, or sigma f is equal to sigma u df du evaluated at u bar. And so there we recovered the same sort of thing that we got from the Taylor series expansion. And so really what the Taylor series expansion is doing, or what propagation of errors in general is doing, is it's assuming that our function over a small range of values can be approximated as a linear function, which makes it easy to relate changes in the horizontal variable to changes in the vertical variable. Okay, and so that's what we're doing. We're doing like a linear approximation to some arbitrary function f of u. And it's valid as long as this span of values is not too big, such that this linear approximation breaks down. Okay, does that make sense? Yeah, okay, I'll assume it makes sense. Okay, good. So now we want to get a little more complicated and say, all right, that's fine for a function of one variable, but we started with an example where Boltzmann's constant was going to depend on both slope and temperature that both have uncertainties. And so what do we do in that case? All right. So for a function of, well, okay, function of more than one variable. All right, so y is going to be f of u and v, and you could throw some other things in there if you wanted to. All right. The first order Taylor series expansion is, okay, so y is equal to f evaluated at u bar, v bar, and the average values of any other variables you've measured. So that's the, that might be the 0th order approximation. To make a first order approximation, we're going to keep some more terms here. So we're going to have, just like we had before, u minus u bar times df du evaluated at u bar. But now we have to include plus v minus v bar df. Oh, I should use partial derivatives, shouldn't I? Now we have a function of more than one variable, so I'll write this as partial derivatives. So this is going to be df dv evaluated at v bar. And then if you had more variables like a w or something, you'd have a term like that. I'm not going to include any higher order terms. Like higher order terms would be like u minus u bar squared times the second derivative, and then there would also be 1/2 factorial, things like that. But we're not going to include those types of terms. Okay, so let's see. If we assume, now the argument is pretty similar to what we did for one variable. We assume that f at u bar, v bar, and so on, we could write as f bar. Okay, so then we would have, let's see, if I want to be consistent with my previous example, y would be a function. Oh, I don't know what's happening here. Y would be a function of u, v, and so on. Okay. So what we could do is we could take f minus f bar is equal to all this stuff. And then we're going to calculate the standard deviation of f. We're going to find sigma f. So therefore, f minus f bar is approximately equal to, let's see, u minus u bar df du evaluated at u bar plus v minus v bar df dv evaluated v bar, and maybe some other terms. All right. So sigma f squared then is going to be approximately equal to 1/n minus 1 times the sum of I equals 1 to n. Okay, so now we have to think of, like, we have these individual calculations of f. So these f sub i's minus f average squared is going to be equal to 1/n minus 1 sum of I equals 1 to n. Okay, so this thing we're going to replace with all of this stuff. So we're going to have to write kind of a few terms out here, I guess. So ui minus u bar df du evaluated at u bar plus vi minus v bar df dv evaluated at v bar plus more terms and all of that squared. All right. Now, what we had before was just that first term, and when we squared it, we could just square this and square that, and that was nice. we have a complication now because I will get a term that is this squared times this squared and this squared times this squared, but we'll also have cross terms where we multiply this and this. Okay, so let's write it all out. So therefore, I'll try to write a little smaller because we're going to have a bunch of stuff here. 1 over n minus 1 square sum of I equals 1 to n of, okay, let's see. ui minus u bar squared df du evaluated at u bar squared plus vi minus v bar squared df dv evaluated at v bar squared. There would be more terms like that, like maybe a w term, an x term, a y term, and so on. And then we're going to start getting these cross terms. Okay, and so when we get the cross terms, we'll end up with it should be 2 ui minus u bar, vi minus v bar, and then the product of these derivatives, df du at u bar times df dv at v bar. And there would be more cross terms if there was other variables besides u and v. Okay. No, it's not a double derivative. It's a product of 2 first order derivatives. Yeah. Okay, so there's some nice things here. If I distribute the sum, this first term is exactly like in the other example. This is just going to be sigma u times this derivative. And this one's just going to be sigma v times this derivative. This thing is new, right? So we'll have to handle that with a little bit of care, I suppose. So what we'll do is we'll say the sum of I equals 1 to n of 1 over times 1 over n minus 1 of u minus u bar. That's going to be sigma u squared 1 over n minus 1, the sum of I equals 1 to n of vi minus v bar is going to be sigma v squared. So this is sigma squared, standard deviation squared. Does anyone know what that is typically called? Variance? Has anyone heard of variance? So variance is typically called standard deviation squared. So this is the variance of u, and this is the variance of v. This thing here, the product of these two is called the covariance. So let's define the covariance. Sigma uv squared is going to be equal to, well, okay, I'll write it over here. Give myself a bit of room. It's going to be equal to 1 over n minus 1 of the sum from I equals 1 to n of ui minus u bar times vi minus v bar. Okay, so instead of having a single one of these variables squared, we have a product of that difference for 2 different variables. So in that case, we would say that sigma f squared is going to be equal to sigma u squared times the derivative of f with respect to u evaluated at u bar, and then the same thing for the v variable. So I forgot a square here, so the derivatives get squared. And then there might be more terms like that for w and so on. And then we're going to have this covariance. So we're going to have the covariance times the product of 2 derivatives, one with respect to u and one with respect to v. So this is going to be sigma uv squared. Remember, there was a factor of 2 for our cross-term multiplication. And then we have df du evaluated at u bar, df dv evaluated at v bar, and there might be more covariance terms hanging around. Now, in the last example, you correctly pointed out I could just take the square root of all of this. So now it's not so simple, okay? This is kind of okay. It's a bit ugly. This covariance thing is unpleasant. So I want to think about that a little bit. If these variables u and v follow a normal or a Gaussian distribution, what would happen if I took the sum of all the individual measurements subtracted from the mean and I added them all up? What would I get? 0, right? Sometimes, like half the time, this ui will be less than the mean, and half the time it'll be more than the mean. And so I'm going to be summing up some negative numbers and some positive numbers, and they're just going to sum up to 0. Same thing for the v variable, and in fact, same thing for the product of the two. So if your data follow normal Gaussian distributions, this covariance should vanish. So if the measurements of u and v follow Gaussian distributions, that's the same thing as saying is if the uncertainty in your measurements is completely random, so there's no preference for measuring something above the mean compared to below the mean, then the sum of ui minus u bar will be 0, and the sum of vi minus v bar will be 0. And in fact, the sum of their product will also be 0. And all of that would mean that the covariance sigma uv squared would equal to 0. And so in that case, we're going to assume essentially that every measurement we do obeys this kind of behavior. And in that case, the uncertainty in your calculated value of f is equal to, well, I'm doing the square of that. The square of the uncertainty in f is equal to the square in the uncertainty of u times df du evaluated at u bar squared plus the square of the uncertainty in v df dv v bar squared. And if there was like more terms, they would look exactly the same for whatever those variables are, w or something like that. And so this is the propagation of pairs. Okay, good. So what time is, have we gone over time already? Yeah, okay, sorry. Sorry about that. So what we'll do is next time when we come back from the break, maybe we'll just finish off that Boltzmann's constant example just so that we can wrap this up in a nice little bow. But this is the sort of thing that we should be using from now on in the lab. It'll be a little more clear once we do that example Monday when we come back from the break. So enjoy your break and we'll see you in just over a week from now. All right, thank you very much.